Hi, welcome back to the breadboard. One of the things in many of my previous videos I've promised myself to do is to build a DC load. And every single time I've built or done something with the power supply, especially the power stage, or tested various other switching power supplies and things that have been sent to me for review, I've had to cobble together a little NPN power transistor or MOSFET or something to drive it from a signal generator to try and get some kind of DC load and output characteristics at the power supply, which it works well enough, but it's been a bit of a pain. So what I decided to do was to quickly put together a design for a DC load that I can put into a little project box that's relatively easy to build and is doable from all of the spare parts that I have lying around in the lab. So what do I want this thing to be able to do? Well, I want to be able to have it handle easily up to 30 volts or more and up to about 5 amps of load. I want to be able to drive it from a 5-volt signal external, which could be from a digital to analog converter or from my arbitrary waveform generator or something like that. The reason I picked 5 volts is because that's relatively easy to get out from a D to A converter on pretty much any controller or standard DAC from Texas Instruments or other vendors. The other thing that it can be, why that's a good voltage to use is because I have some Ref02 standard voltage references that I can also put on the board that give out a very stable 5 volt that I can use to feed into a potentiometer so that I can use manual settings as well as automatic. So I'm going to include a switch in the circuit so that I can switch between the manual potentiometer setting and the signal input from an external source. One of the other design criteria that I have for this is I want to be able to just run it off of a DC 12 volt adapter just from a wall wart. That gives me the isolation I need and makes it easy to power it without having to have any issues about mains and things like that. You can pretty much take any 12, 15 volt, it really won't matter in this case, supply and plug it in and it will work. So the MOSFET I'm going to use for this is the same ILF P640 that I got from Element 14. It can handle plenty of load and plenty of volts, so there's no issues with that. The one limitation that this thing will have, however, is the power dissipation. I've already tested on the breadboard going down to a lower supply as about half a volt. Actually, I went down to about 0.3 volts going as the DC source that I was loading. Now, at that value, I can't drive 5 amps because I'm using a 0.1 ohm current shunt, which gives me 100 millivolts per amp. So at 5 amps, that's 500 millivolts. So obviously I can't drive the full 5 amps if I've only got 500 millivolts coming into the circuit. There'll be nothing across the power MOSFET. But I can drive an amp with only 300 millivolt source voltage as well. So that's pretty good at the low end. I also want to be able to crank this thing down to just a few milliamps if I can. I'm going to run it off of a single supply, which pretty much negates being able to get down to completely zero. In order to do that, I would have to run the op amps with a split supply. Even with op amps that are rail to rail, they're often, because of the limitations of things like the manual potentiometer, which very rarely do you actually get a zero resistance at one end of the scale. You can never quite get to the zero, so that's fine, and it'll still meet the criteria of what we want. It may be another video where we do a precision low current DC load or something like that, but for what we're doing here, up to 5 amps, I think if it can go down to just a few milliamps on the low end, up to 5 or more amps at the high end, then that'll be great. Another feature I want to put into this thing is the ability to just tweak the high end of the 5 volts from to the potentiometer. That allows me to scale the pot so that I can go from fully wound one direction to get as close to zero as I can, and then fully wound at the other end to get pretty close to 5 volts. So by putting the trimmer across the RefO2 voltage reference, I can actually either increase or reduce the voltage slightly on the output of the VREF to compensate for any discrepancies in the op-amp or the potentiometer from getting the maximum current out of this thing. So anyway, let's go have a look at the circuit diagram that I've done, and then we'll go look at see how it works on the breadboard. Okay, so here's the schematic I came up with. This is probably going to look very familiar to many other DC loads that are out there. On, if you Google DC load and things, you're going to find plenty of schematics for them, and they're all basically going to look fairly similar, because at the end of the day, all you need is an op-amp to drive a MOSFET or a power transistor, a current sense resistor, and an adjustable voltage to feed into the op-amp. And the current sense resistor acts as part of the feedback loop, and therefore that basically constitutes your adjustable DC current load. Now, what I've done is I've extended this to just suit the criteria that I want, in that I want to be able to have an external input to feed into this. I've DC coupled it because I want to be able to not only inject varying signals, either sine wave, square wave, well, pretty much any shape I want, but I also want to be able to adjust the offset from 0 so that perhaps I can set up a 2.5 amp load, but then have some milliamps of noise or anything else that I might want to introduce onto the unit under test. So this could be a battery or something else. So it's going to be DC coupled, and I want to have it as 0 to 5 volt, because then I can drive it from numerous different devices with relative ease. The input I want to have as 12 volts. I've put a diode in series with the input, just in case you accidentally connect it backwards. Now, connecting a low voltage on this is going to do no harm at all, and these RefO2s and also the op-amp that I've chosen can go up to about 30 odd volts on the input. So your power jack here can be 12 volts, 15 volts, 20 volts. It won't really matter, it'll all work just fine. So that's nice. I haven't put any other protection on the input except for a about 100 nanofarad capacitor for high frequency decoupling, and about 100 microfarad capacitor for just localized smoothing of the power rail. I'm feeding that input directly to my op-amp. Well, I've got a dual op-amp being used here. It's just a TLC 2142. You can pretty much use any op-amp you like. Now, pick one that can go rail to rail, at least on its inputs, because we're gonna be varying this. If we want to, the MOSFETs, their voltage gate source threshold is typically between 2 to 4 volts. So as long as this point on the control, as long as the output can go below 2 volts, then the MOSFET's going to get turned off. On the high side, it's only ever going to go as high as the supply that you fed it. Now, because most MOSFETs, in order to turn them hard on with higher voltages, you need to take this input to often about 8, 10, 12 volts on the supply here going into the gate. There's no real current here, but the resistor is just a little bit of decoupling, because the FET actually typically acts as a capacitor on the gate to the source. So it just helps to reduce a little bit of ringing. The one thing you'll also notice here is that my DC load, which is going to be connected via some banana jacks, is completely separate to the analog control circuitry here. I've got a 4-terminal current sense resistor that I'm using. It's a Vishay R100F. It's only a 1% tolerance resistor, which is perfectly fine for what we're doing. But what it is, it's using Vishay Precision Group's bulk film technology, and as a result, it is extremely stable over temperature swings measured in the few parts per million deviation. So it really, even though it's a 1% resistor, I've said in many videos before, the accuracy is not what is important. What is important is stability, because by including a trimmer on the 5 volt supply here, the 5 volt reference, sorry, the RefO2, I can set this up such that by measuring the current flowing through here with an external meter, say a 4.5 digit meter or something, I can actually just tweak the VREF with the pot turned to maximum so that I get exactly 5 amps flowing through here. That basically then is immediately compensated for the feedback when I'm using the 10-turn pot. Now, obviously that doesn't compensate for if I fed 5 volts exactly into here, that it would be exactly right from the outside source. Now, you could, again, put an additional adjustment pot or something like that if you wanted to as well to get that more precise too, but we're trying to keep things fairly simple here. And when we start using this external signal, the primary purpose of that is so that I can start putting noise and testing transient response and things like that. And when you're trying to do that, you really don't need to worry about it being absolutely precise. You know, you just want to go between 1 and 3 amps or 2 and 5 amps or whatever it is you want. And it, you know, the millivolts or milliamps differences really are not as critical in that kind of situation. And right now, the circuit that we're building here and that I'm going to put into this project box is not going to be, you know, it's not going to be computer controlled. It's not going to have any of those fancy features where you can have program, you know, to keep a constant resistance or a constant voltage with current and, you know, a constant power on the output or anything like that. Sorry, all my meters are slowly turning off here. I will later on do another DC load project where we will have a microcontroller involved and we'll have feedback into analog to digital converters and things like that. And in order to be able to do that, we'll probably go into using differential measurements and things, because you want to be able to measure the output voltage, you want to be able to measure the current that's currently going through and things like that. In this particular circuit, I'm not going to bother, well, I may not bother putting any meters on. I do have some little panel meters that I've shown you in previous videos, that, you know, little things like this, which I may just put into the case for the sake of monitoring maybe just the current or something. But what I am conscious of is potentially interfering with the control by introducing extra ground loops, because these things get powered from 12 volts quite easily, but the 0 volt on the current is the same as the 0 volt on the supply. They're not isolated from each other and they're not differential, so they can potentially give some interference. But I think what I might do is just see in the testing if just putting one of these on for maybe just the current might be enough to give us a good reading, because we really don't need to have you know, the voltage unless you want to start monitoring how much power you're dissipating, because like I said before, the main restriction on this circuit is not on this analog side. This is pretty straightforward. You know, it's going to be able to drive, you know, I could make this drive 10 amps if I want quite easily by just adjusting the feedback resistor. Instead of having a 100 milliohm, if I simply change that to be a 50 milliohm, then this circuit instantly becomes a 0 to 10 amp without changing anything else in it whatsoever. So that's something that's maybe worthwhile having even as a switch, maybe, so that you can flip between one current sense resistor or another. But the biggest issue we have here, which I keep alluding to, is actually the MOSFET transistor. I'm using the IRFP 640, which has, you know, something like 70 volts or a very high voltage and very high current capability. I can't remember on the spec sheet, I don't have it to hand here right now. Way more than enough that we need for here, but that's not the issue. If I have 5 volts across here and I'm drawing 5 amps, that's 25 watts. That's still quite a bit of power to dissipate in a heatsink. And, you know, a reasonably small heatsink may do the job, but it's going to get pretty hot. Now, if I then take this to, say, a 30 volt supply and I start pulling 5 amps through it, now I've got 150 watts that I'm trying to dissipate, and there's no way that a small heatsink on its own is going to be able to deal with that. In fact, even the RFP 640 may not have enough capacity to quite handle that level of load. So you'd have to pay attention to what you're doing for cooling and everything else, and maybe even parallel up 2 of the transistors just to allow better heat transfer to the heatsink. Now, That pretty much covers the whole circuit that I've got here. Okay, what we've got, as I say, quickly running through it again, we've got a 5-volt voltage reference powered by the 12 to 24 volt kind of input. We've got a buffer for the 10 turn potentiometer that I'm going to use to feed into the driver stage. I've got an external switched input. I've got a 10 to 1 divider here. Because I'm using 100 milliohms here, that basically gives me the 500 millivolts feedback. So I've got a 9K and a 1K precision resistor. Again, these are Vishay resistors that they kindly sent me as samples to have a look at and review. And one of the nice things is these things are so precise that you can put them in and not even worry about how, whether they're 9K exactly, because you can get these things to several digits of accuracy, and they will even trim resistors for you to exactly the value you want, up to about 7 digits of accuracy if you really, really want that level of accuracy. So then we've got our op amp that's just basically taking it. Now remember the theory with an op amp, I'm applying say 100 millivolts on the positive input. The op amp will do whatever it has to do to get its negative input also at 100 millivolts. So it's going to drive this output high through the 10K to the MOSFET. Now the 10K from a DC perspective is relevant here because the MOSFET is only going to be drawing nanoamps, if that, into its gate as leakage through between the gate and the source, so it's really negligible. Then you're going to have your current flowing through on the high power side of this and back out, inducing a voltage on your sent resistor, which is 100 milliohms. So as soon as this 100 milliohms gets 100 millivolts across it, that would indicate that it's drawing 1 amp. That 100 millivolts is going to feed back through here to the negative input. It's going to balance out the op amp, and the output is going to stabilize at some voltage that's going to keep the two sides of this equal. Now this capacity here that I've put in here going right back from the negative input and from the output is to reduce noise, because there's obviously a certain latency between setting your voltage, the output responding, the MOSFET responding, and the feedback coming back to this. And if you didn't have some kind of feedback to limit basically the slew rate of this thing, it's going to start ringing like crazy. And I can actually demonstrate that on the breadboard by simply removing this, because technically from a DC perspective it should all work fine, but when I take this out you will see that it will actually start oscillating quite severely. So only 47 nanofarads or 100 nanofarads or something is all that you require in here. I just picked up a random one from my bucket of spare parts, which I think was 47 nanofarad, and put it in, and it completely killed all of the oscillations, so that was great. The other way you could do it is potentially put it between the output of the op amp to ground, but then what you've got is you've got high currents flowing through out of the op amp while the output is trying to get to its correct value, and that's really not a good idea. So including in the feedback is the way to do it, and then having the 1K here limits, so when the output goes up, basically it's going to bypass the feedback loop over here back to the input and limit the gain for the transient response. And the same on the output here. If I suddenly change the voltage, the output's going to try and increase very quickly, and it may overcompensate in the other direction. So again, this capacitor will limit the rate of change in here. So if you remember the previous video we did where we looked at integrators, well, that's kind of a integrator in its own right, and it's going to limit the rate of change for us. It's not fully working as an integrator, it's just being part of the feedback loop, where it's basically limiting the gain at high changing of either the input or the output. It's just limiting the response time for it to basically stop the oscillations and things. Anyway, that's pretty much the entire circuit that there is. As you can see, it's relatively simple. You've got one 8-pin dip reference chip, you've got one op amp, dual op amp, and you've got a handful of passive components. Now I've used precision resistors for this, and I've got a fairly good quality current sense resistor here. So these two items, the sense resistor is probably about $10 on its own, but you don't have to use one like that. If you really don't want to be measuring very, very accurately and have maybe 4 digits of accuracy, then you could just put a 100 milliohm resistor on here, solder the main current path to the outer sides of the axial leads, and then solder your sense leads close to the body of the resistor as you can get, and just hook that into your circuitry, and it will probably work well enough for most things. The key, as I keep saying, is the stability of these components, not the accuracy of them. So really whatever you get, even if it's a 5% or even a 10%, if it's stable, like 10 parts or 50 parts per million or even 100 parts per million, then you can compensate for the rest by using little trimmers and things like that. I mean, if I wasn't wanting to use an external source here, and all I had was the output of this, then this trimmer would allow me to set the high end to be very, very accurate. And by using a 10-turn potentiometer here, I could set that output quite accurately to what I want. And I actually have some old dials that I've had since I was, well, I've had them for a long, long time, probably 30 years at least, 40, maybe nearer 35 years. And what they do is they go on the front of one of these 10-turn potentiometers, all right, like this one I'm going to use here, which is a 50K one. And it actually gives you a 3-digit reading between 0 and 100%, which would allow very accurate setting. Now we've got it set at 5 amps here, but if I do change this resistor here down to a 50 milliohm, then this 0 to 100 reading on the dial for this thing would basically give me the 0 to 10 amps with a dial setting of basically it's got 3 digits on there and then 1 full rotation of the last one. So that basically gives you effectively close to a 4-digit adjustment accuracy on that 10-turn pot, which is pretty good. So we'll have a look at how well that will work for us. And I may even change this thing to use up to 10 amps of load capacity so that we can test batteries and things like that. I'll just have to be cognizant of how much heat will be potentially generated in the load while we're doing it. Anyway, let's go and have a look at the circuit now, so we can have a quick look at how it's put together and how little there is. Oh, the only other thing I've included on here is I put a little 10K resistor and a small LED so that I can see when I've got my circuit powered up, because I kept forgetting. And I've got a whole bunch of things hooked up to my breadboard right now so that we can measure all different points of the circuitry while we're testing it. I've got my signal generator, my oscilloscope, my Keithley power supply is acting as my DC source right now, and I've got 4 meters all hooked up ready to do this. So let's just get this out of the way and we'll start looking at this and how it performs. Okay, so this is the breadboard with everything made up. The chip in here is powered up, so I'm just going to be careful where I poke my screwdriver. The chip in here is the REF02 that gives us our 5-volt stabilized output, and it's only got a few parts per million drift. We have our standard dual op-amp here, which is doing, one side is just acting as a impedance converter for our potentiometer. The other side is the drive circuitry. What we have here is the 3 wires that are going out to the power MOSFET. 2 of the wires here are the sense resistor coming back to feed into the op-amp, and the green wire, I've kept it green for gate, is the feed to the gate of the MOSFET. So what I have here is the op-amp channel 1 on the dual op-amp. The output is feeding via 10K to the green lead going up to the MOSFET. The feedback on the high side is the yellow wire here from the shunt resistor. It's coming through the 1K resistor, if you remember on the circuit diagram a moment ago, to the negative input of the op-amp, and then this capacitor here is the 47 nanofarad decoupling between the output and the input to basically limit the rate of change on the op-amp. This capacitor here is just, I don't know, 100 microfarads or something like that I've just put across the supply rail for high-end decoupling. This one here is the 47 to 100 nanofarad capacitor just for higher frequency noise decoupling as well. Here is the trim pot. All I had was a 50K trim pot. The actual manual for the REF02 says put a 10K between the rails, but I don't have any 10-turn pots or anything like that either. So what I've done is I put 100K from the 5-volt supply, the 12-volt supply to one end of the pot, and I put a 10K to ground. That limits the range that this will adjust so that I can basically tweak the output of the REF02 enough. I've actually put an order in to get some 10-turn pots, but of course they're going to take a few days to get here. The other thing we've got here is that these are the 2 precision Vishay resistors. This one here is a 90K. which is taking the output of the potentiometer through the buffer of through the op amp. Of course, it's taking that 0 to 5 volt range and it's dropping it down between this one and a 10k. So you got 90k and a 10k, which makes the 100k, which gives you the exact 10 to 1 divide. You know, the 1 volt out for 10 volts in, or in our case 5 volts in, gives us 500 millivolts out, very, very precisely. And then that is fed to the input of the second op amp, so that we can drive our load. And of course the open loop gain of this is controlled because of the sense resistor and everything else. The input of the 10 to 1 divider is going through a switch, which I have down here. All right, so I've got my potentiometer controlling 0 to 5 volts. I've got a switch, and then over here I have the coaxial input from my signal generator. So I've got a 10k ohm load across there, just so that if you don't have it connected and you switch the switch, it's not going to leave the op amp input just floating like crazy. What I will do is I'll put that on the board, but just for now I connected it on the BNC connector. So that you've got the BNC input feeding to the switch, you've got the other side of the op amp low impedance feeding into the switch. The output of the switch is feeding back and going into the second half of the op amp here to drive the load. So that's exactly what we had described in the schematic that we were looking at a moment ago. So let's just back this out. And there's a lot of clutter on my desk here because I'm working on the power supply project as well. But I wanted to just take a quick deviation from that so that I could build this little DC load up. Okay, so what I have here, I'm going to do a DC check first, is I have my U1273 is directly measuring the current flowing from the power supply. The U1461 here is measuring the volts across the DC load. So this will be the equivalent of your terminals on the front of your DC load unit if you put some banana plugs on there or something like that. It's going to read slightly lower than what my power supply is because I've got the burden voltage of this meter as well that's in series with it, of course. So my power supply is reading 6 volts right now, and this is reading 4.89. So I'm drawing about an amp, so I'm dropping about 100 millivolts across this meter. This meter here is measuring, let me just re-verify what that's measuring. That's measuring the output of the potentiometer on the op amp. So what I've got here is that one is connected right here, which is measuring the output. So we've got the 10-turn pot here, and it's measuring pin 7 right here. So we're testing here so we can see what we're setting the pot to see how accurate it reflects the output. And the last meter here on this side is measuring the feedback from the current sense resistor onto the negative input of the op amp. I've got the input volts on here set to 1.0006, and as you can see we've got 1.0015, which is pretty good, and our current shunt resistor is reading 1.001 as well. Well, 100.1 millivolts, which tells us that everything here from a DC perspective is working quite happily. And if I start tweaking down the volts to all the way to 0, right, so that's basically sitting at 0 now. We've got 400 microvolts sitting on the output of the on the current sense resistor that tells us there's a tiny bit of current flowing through here. We've got 6 volts now. Because there's no current, then obviously the shunt resistor is having no effect, and nor is the burden voltage of the other meter. And you can see we have basically 6 milliamps of current flowing there. So there's a little discrepancy between the two right now, but that's just still within the tolerances of the meters, and the current shunt resistor is a 1% current shunt. So it's not surprising it's just a little bit out, but that's okay. So yeah, 6 volts, we've got 30 millivolts basically on, 3 millivolts on the potentiometer. That's as low as it can go. Remember what I said at the very beginning, not all potentiometers, in fact very few of them, can actually truly reach the 0 ohms on their input, which is why in this case I put the buffer after it and before the potentiometer is before the divide by 10, so that any low end errors on the potentiometer are basically reduced by 10 as it goes through that divider network. So okay, so low end, it seems to be fairly stable. We'll have a look at the oscilloscope in a moment. So let's just crank this thing up to the full. So we'll go up 1 amp at a time, or a half an amp at a time. So we're set to, we'll base it on what the this meter here is reading. So that will set that one to exactly 500 millivolts, which should reflect 500 milliamps. So that's 500.000. I'm reading 502 there. My power supply says I'm drawing 503. So I'm only 3 milliamps out. That's not too bad at all. And my current shunt resistor is reading 501. So again, within the tolerance of the meter and things, that's pretty accurate for what we need. Let's go up to 1 amp. Close enough. So we've got 1.0013, we've got 1.002 reading on the true direct reading of the current, and we've got 1.002 on the feedback as well. So that's actually tying up almost exactly. I'm reading 1.002 amps. I've got 1.002 amps being read on the shunt as well on the feedback, and I've got 1.001 going in, so that's pretty good. Let's jump it up to 2 amps now. There we go, 2 amps. Well, close enough. So 1.999, 1.999, 1.9981 actual amps. That's pretty damn good in my book. Let's go up to 3 amps. So that's 3.001, 3.003, we've got 3.001, 3.003 here. I would say that's pretty good as well. My heatsink is starting to get a little bit warm. Not surprising, because we've got 5.5 volts at 3, so we're actually dissipating now about 15 watts here. So that will start to get toasty on the power MOSFET. The actual current shunt resistor, it's negligible. I mean, even at maximum load, it's still only 5 amps into 100 milliohms is only 500 millivolts. So 5 amps at 500 millivolts is only 2.5 watts. So that's more than capable of handling it bolted to a heatsink at maximum power. So let's crank it up to 4 amps. Okay, that's 4 amps. We've got 3.995, 4 on here, 4 on the power supply, so that's good. And we'll crank it right to the top. That's basically as high as this thing will go. And we've got slightly over, we've got 5.02. That's just, I can obviously adjust that down. What I want to ultimately do is have the pot so that when I hit the top it's exactly right, and I can use my trimmer for that. So I just backed it off a little bit so that we have 5 volts on the 5 volts on the potentiometer, which gives us 500 millivolts going into the power circuitry. We've got 5 amps pretty much exactly. And we've got exactly 5 coming out of the power MOSFET, the shunt resistor. So, yep, and that is starting to get to the point where I can't touch it. I actually haven't shown you how I wired this up yet. So let me just pan the camera down so that you can see how this is wired. So here is the power MOSFET. So I got the power MOSFET bolted to this heatsink. I've got my shunt resistor here, and the output of the power MOSFET, the source end, I've got a heavy gauge wire going directly to the current shunt resistor, and then the output of the current shunt resistor coming through to the terminal on this black wire to my banana jack just down below the bench here slightly is about 6 inches of wire. The brown and the yellow wire here are measuring the voltage across the current shunt resistor, and obviously they're not part of the high current path. So they do not get any voltage offsets due to current load, because these are going into high impedance inputs on the op amp, so there's virtually no current draw through there, so therefore you're not going to get any voltage drop. And then the gate, which is the green wire, goes to the gate of the MOSFET in here as well, and that's pretty much it. So none of those circuits draw any current, which is why I can get away with using much lighter wire. And obviously this wire will be much shorter if I once I put it in a case and I just shorten it to what's needed. All right, so that's pretty much what's on there. Let's go back to the main circuit. I'm going to crank this current down. This heatsink's getting to the point where I can't hold it. Okay, excuse all the fan noise, but I'm been drawing a lot of power out of my power supply there. So I'm just going to set this to 1 amp now instead. Now, I've got, let's just do a few more static tests first before we go to the oscilloscope and have a look at what that's doing. So I've set 1 amp coming out of the meter, and I've got 6 volts currently set on my DC load. So just to show you how low you can go with this DC load circuit, I'm going to reduce the volts right now on the DC load just to 1 volt. All right, that on the DC load did not change anything one little bit, but you can see here now that my volts on this end, now remember you've got the, sorry, excuse the beeping. Remember you've got 1 amp and you've got basically 100 millivolts or so dropped across this first meter. So what we've got here is showing that we've got 883 millivolts across the DC load, which is quite low, and yet we're still able to maintain the 1 amp. Let's just see how high we can go before it stops rising anymore. This is, remember, this is only with 1 volt. So we've got 2 amps there. So 1 volt, we're able to set quite happily 2 amps on there, and we're getting it. See if I can go to 3 amps with 1 volt. I can. 4 amps. Yep, I can get 4 amps with 1 volt. And yeah, so it's limited there. I'm no longer tracking. So 4.2 amps with a 1 volt source. So if I had a little 1.5 volt battery or something, I would actually probably 1.5 volts would work. But 1 volt load, sorry, 1 volt source that I'll be testing, I can quite happily go up to about 4 amps before it bottoms out. Now that's because there's not enough drive to turn the MOSFET on at that low voltage. But now if I reduce my input on the power supply to even 0.5 volt now, 0.5 volts, all right, now you can see my current dropped a little bit from 3 amps now. It's gone down to a little bit lower. So it's gonna, sorry, we had 4 amps there. It's dropped down to about 2 amps, but I've only got 0.5 volt now, remember that. So let's just go down until it starts to pick up control again. Obviously that's got 2 amps, so we've got to go below 2 amps. Let's just set 2 amps exactly. So there you go, with a 0.5 volt input, I'm actually able to pull 2 amps and control 2 amps through this, which is quite good. Now I know that I can go a bit lower because I was playing with this earlier. So I'm going to go to 0.3 volts input. So that's 300 millivolts source voltage. And it looks like I can go to about 1 amp on that because I've got about 1.2 there. So I'm setting 1 amp now. And as you can see, I'm able to control 1 amp. So that is pretty impressive. That's going quite nicely with only a 300 millivolt input. I'm actually able to draw a full amp out of the power supply. Now that's obviously only 300 milliwatts, so nothing's going to be getting warm now. Things are cooling down nicely. So yeah, static wise, it seems to be doing the job. Now the question now is, of course, what does the output look like? How stable is it? So let's change the focus now to the oscilloscope instead of the DVMs, and let's see what the output is doing here. So I've got this oscilloscope set up. If you remember on our schematic here, we've got our output here, and here's our switch, and we've got our signal input coming in. So I've got one oscilloscope set on the output of the switch so that it's either going to be reading DC, of course, which means I'll have to set it free running. The other output is across the current shunt resistor, so it's zero referenced, unfortunately. So there may be a little bit of offset because of this, but basically I'm measuring across the shunt resistor and also the voltage that's driving into here. And when we start injecting a signal, the reason why I want that is so that I can see the response time from this input change to the output on the current shunt resistor. So right now I'm still controlling it with a DC load, And let me just change the triggering, because obviously on DC it's not going to run very well. So excuse my arm getting in the way there a second. Let's just set for Alright, so I've got 100 millivolts per division on the 1 volt. So basically here's the 0 volt reference line. So that's 100 millivolts, 200, 300, 400, 500. So when I'm up here, that represents 5 amps being drawn. And what I've got on the DC is, I'll set that actually to the same scale. Sorry, I'll set it to 1 volt per division and back it down a bit, because obviously this one is, I'll just back it down to just keep it above it. Just a little bit, just so we can distinguish the two lines. So basically, one is measuring the 0 to 5 volts and one is measuring the 0 to 500 millivolts across the shunt. So now you can see that it's pretty static right now, and I'm going to just sweep right through the range, so you can see that that's at the minimum. There's no noise there at all. I mean, you know, I haven't I could AC couple this. Let me just sweep it DC coupled first, and then I'll put it to AC so that you can see what noise there may be on there. So we're just cranking this up, and you can see it following quite nicely. Oh, I've still got 300 millivolts. Let me just increase the volts. There we go. Sorry, I still had the power supply limited to 300 millivolts. So you can see here we're cranking up. 3, 4. Now there you go. Maximum output 5 volts. We're drawing 5 amps, and you can see there that it's tracking and there is no oscillations. Now remember that capacitor that I mentioned on the feedback to the op amp that was there to reduce the noise of the circuit, oscillations and everything. I'm just going to pull it out of the breadboard here so that you can see exactly what happens when I pull that out. Alright, there you go. You can see this is now broken into some quite serious oscillation. So we've got a 15 kilohertz oscillation going on there, and it's sweeping basically 200 and odd millivolts, which represents, of course, over 2 amps of oscillation, which is quite severe. And if I just simply put this resistor back in from the output of the op amp back to its negative input, you'll see it'll kill it right away. And that's only 47 nanofarads right there. So you can see why that's important to have it in there. It just stops the oscillations and everything quite easily. Alright, so let's switch this to AC coupling on both of these inputs. Or at least the most important one, of course, will be channel 1, but we'll do both of them anyway. That's channel 2. So I'm moving channel 2 up just so it keeps it out of the way of, because we're measuring AC now, so I can do this quite happily. So I've put channel 1, which is the DC load, in the center line. Now I'm just going to tweak now the, alright, so I've set it to 10 millivolts basically. That's the best I can do with the power supply. Now there's noise, of course, in here. If I just set the bandwidth to make sure I'm cutting out any let's set bandwidth limit, and that's set bandwidth limit. Okay. So you can see here that there is a little bit of noise on both of these, but it's only 20 odd millivolts, and it's probably environmental noise more than anything, coming from the where these things are sitting, because one of them, as I said, is measuring the voltage that's coming off of that switch. So there's wires hanging around and everything else loose. It's on a breadboard. And the other one is measuring the output of the current shunt resistor, which is, of course, 5 times less. All right, because remember, this one is the one that goes from 0 to 5 volts. So of the range, that's not a lot at all. So that's 0. Now that's at 0 input. No, it's not. It's at maximum input. So that's at 5 volts maximum input. Let's just crank this all the way down to 0. The AC coupling will compensate. I'm just going all the way down here a second quickly. All right, that's minimal. So you can see the noise there is the same. It's not. I think this is pickup from the environment. It's not actually part of the DC load or anything like that. So let's just slowly go up this 1 amp at a time. So that was 0. Let's go up to 1 amp. Just so you can see that each of the stages here, it's going to be, that's roughly 1 amp. So you can see the noise is the same. 20 millivolts odd noise. Again, as I said, I don't think that's part of the circuitry here. That's 2 amps roughly, no difference. Roughly 3 amps, no difference. Roughly 4 amps, about the same. And maximum current, 5 amps. And that's about the same. As I said, that noise is caused by the environment. If I turn the actual power supply off, right, the actual load now, the power supply itself is completely turned off. So you can see that that noise is still there. It hasn't changed one little bit. If I put the power supply back on, you'll see nothing's changing. So it's certainly not coming from the high current side of anything. And even if I turn off the DC load circuitry itself, and just unplug the power to it, right, now it's completely unplugged. You can see, well, things are floating around a little bit now, but that noise is exactly the same. So it's coming from the environment here in my office, unfortunately. But nevertheless, if you just ignore that, try to, you'll see that this is working quite nicely. So let me just power these meters back up again. Excuse the noise. I just need to be able to see what they're reading. So I'm going to crank this down again, and we're going to switch to using the signal generator. Okay, so the switch, I'm just going to flip it over now. I've currently got it set to 100 hertz, 5 volt peak, and 2.5 volts offset, which basically means that I'm feeding a square wave of 0 to 5 volts input to that op amp through the divider, which means it's going to be switching from 0 amps to full 5 amps 100 times a second. Let's go. Alright, so we got lots of gain here. Let's turn off the AC coupling, and we'll crank up the volts per division as well, so that we've got a sensible value here. So that's 2 volts, 2 volts. And let's reduce the frequency so we can see. Okay, now obviously channel 1 is not 2 volts, it should be 200 millivolts to keep it on the same scale. So that's the, let's just bring it down a little bit. Bring this one down. Alright, so the blue line that you're now looking at here is the signal from the from the Agilent frequency arbitrary waveform generator, and you can see there it's generating nicely 100 hertz, and it's a nice square wave going from 0 to 2, 4, 5 volts peak. Okay, the yellow line is the output of the DC load, and you can see that it's got some level of slew rate here. It's got a minor overshoot on the current. Let's go down to 100 millivolts and adjust the scale so we can see a little better. And we'll increase the time base a little bit. Look at the edge. Alright, so now you can see here quite nicely what we've got. There's a little bit of lag as we switch down, but we're still talking about only, actually let me just try and adjust that and we'll get a decent measurement. So I'll line that up on one of the graticules. There we go. So we've got almost an instantaneous change on the input. Remember, we've got that feedback capacitor that's short-circuiting the gain as basically a little bit of an integrator. So we've got a slope here on the rate of change of the output, which is still a half a millisecond, which is not too bad at all. And then, you know, there's a little bit of adjustment as we float through here. This is when it's off, and then we turn on again. There's a tiny bit of overshoot of probably 10 millivolts or maybe 100 milliamps before it settles down. Now remember, we're switching very, very sharply on our input, and we're going from 0 to maximum load on and off, on and off. And there are no, we've got wire lengths, quite long wires, probably 3 feet of wire from the power supply to the input of the terminals of the DC load circuitry. So all of that, the inductance of that and various other things are going to cause some of these effects. If we were able to dramatically shorten this, maybe use a battery or something like that, very, very close to the control circuitry, you'd see a lot of this stuff disappear. So I'm not actually too worried about that response time. And as you can see, we can, that's 100 hertz. That's not something you would be normally doing, banging against the rails at that kind of speed. If I reduce this down to 10 hertz perhaps. All right, let's just crank this down a little bit. All right, now on that scale you can see it is doing pretty good. There's no noise on the top or the bottom to speak of, and it's tracking very nicely with this. Now if I change this to a sine wave, so now you can see there is no overshoot or anything like that. Of course it's a sine wave, so it's giving it a nice input, and it's tracking very, very nicely between 0 and maximum load. I can probably increase the frequency of that now without any ill effect. So that's 100 hertz. All right, there's a little bit of distortion on the bottom here where it's approaching 0. Probably because the op amp and things like that is probably, I haven't used necessarily a rail-to-rail op amp for this, I don't think. I'll have to check. But anyway, it's understandable there. If I actually reduce the amplitude by, instead of going 5 volts peak to peak, let's go, let's just take it to 4 volts peak to peak, and we'll see if that disappears. Yeah, see, that's cleaned up nicely now. It's completely gone, because it was hitting near the low rails that we were getting the issue. So now if I probably increase this even to 1 kilohertz, right? So that's 1 kilohertz now. We're probably going to find that it may lose some of its dynamic range for this. Actually, let's just back off and compare. So that's got 1, 2, 3 divisions there. So let's go back to 100 hertz. All right, so that's, yeah, it's starting to clamp down, probably because of the capacitors and various other things. It's the time to respond is slowing down, because now we have 1, 2, 3, 4 divisions, which is what we would expect, because we're putting 4 volts change, which means we're varying it between 0.5 amp and 4.5 amps. But increasing the frequency to 1 kilohertz, obviously the output is not going to be able to respond quick enough now. And that's actually okay. We don't want it to be. And you can see now, actually, that's one of the other things that I was talking about, why the dampening is required. Now that I'm changing it so quickly, you can actually see that there's some phase shift here, quite significant between the input and the output following and changing it. So if I increase that frequency to 2 kilohertz, it's probably going to change even further. All right, so my input is still going basically 4 volts, I think. Yeah, 4 volts, which is exactly what we want. Obviously, it's sitting with an offset, and you can see now that the output has shrunk a little bit further, and its phase shift has gone even further. So that's 2 kilohertz. Let's go 3, 4, 5. That's 5 kilohertz now. And you can see the output now is really not. If I AC couple that one, probably might make it easier to keep it on the screen, so I can increase the amplitude. All right, so that's increased its phase, and obviously it's shrinking. So it hasn't got a high frequency response, but you probably don't even need it to be that high a frequency response. If you do, then maybe you'd have to go to some more advanced circuitry and things like that. But let's just crank this up to 10 kilohertz just to complete the picture out of interest. So we've still got the 4 volts going in, and we're almost 180 degrees out of phase now. Oh, well, getting close to, and we're getting a little bit more noise being present there. But let's go back to something more realistic now. Let's go back to 10 hertz. All right, so that's 10 hertz, and you can see now the The phase is probably the same, it just isn't noticed now. Of course, one of the other tests you can do, that's one of the reasons I did the DC coupling with this, is so that I can input a variable frequency signal, but also have a DC offset, so that I can have like a 3 amp base current and put a half an amp of noise or something like that onto it. So what I can do here, for instance, if I go to change the waveform instead, and I'm just going to go and pick noise this time. All right, so that's now injecting noise. I've got an amplitude of, let me just change the amplitude of the noise for a moment. The noise amplitude is 1 volt, which will represent 1 amp of noise. And right now that's sitting with a bandwidth of about 1 megahertz. So let me just change the frequency of the noise down to something more reasonable, like let's just say 100 hertz. So twice mains frequency or something like that. All right, so that's now introducing noise at 100 hertz, 1 volt peak to peak, and I've put a base offset of 2.5 volts. So that's basically sitting there with 2.5 amps flowing, and I've got 1 amp of noise being introduced on it, and you can see that it's actually keeping quite happily up with it. Of course, I'll probably have to switch these back to AC coupling to bring it on the screen. There we go. Set them both to the same relative scale. So you can see there's the noise, and you can see that it's actually tracking quite nicely. So I'm quite happy with that circuit. I guess the next step is to now put it into a case. I guess what I will show you before I go on is everything we've been doing up to now has only been using a 5 or 6 volt input, which is what we're looking at on the scope and everything as well. So just to show you at the high end range that this can go there, and I won't be able to stay there too long because, as I said, this heatsink is going to get rather toasty, is I'll flip back to the static DC input, and we'll actually go and connect the power supply to the 30 volt output instead, and see how that tracks. As I said, it's going to get quite hot, so I won't stay with the relevant voltages very long. But let me just switch things around. Okay, I've now got 30 volts set on my power supply, and I've got the current set to 0. So as you can see here, I've got 5 milliamps at 30 volts, which of course is going to be nothing across this because that's no power, no load whatsoever. And you can see I've got 400 microvolts showing on my meter for the shunt resistance, and I've got 3 millivolts from the output of the potentiometer. Sorry, had to think there for a second. So okay, let's now crank this up. Now I'm only going to be able to draw about 1.5 amps out of the power supply at that, and that's going to be 30 volts at 1 amp. That's going to be about 30 watts being dissipated in the heatsink, so it's going to get quite warm quite quickly. But let's go up initially. Let's set ourselves a 0.5 amp. All right, so there's a 0.5 amp roughly, and that's confirmed on the power supply, and that basically now is 30 volts. As you can see, we've still got 30 volts less the burden voltage at 0.5 amp, so we're dissipating about 15 watts already in the heatsink, or in the MOSFET. So now we can go, and it's obviously tracking quite nicely, and we can go up to now to 1 amp. Okay, so there's our 1 amp setting. We've got 1 amp flowing, we've still got 30 volts, excuse the beep. I can go up to 1.5 amps on the power supply. So I'm just going to take that up the extra 0.5 amp. The power supply is just dropping in and out of current limit now. Trying to back it, I've just backed it off a little bit. So you can see there we've got 1.5 amps. So basically now we're going to be piling a lot of heat out of this MOSFET because all of it's being dropped across that MOSFET. That's about 140 millivolts across the power resistor, the current sense resistor, which is really negligible power wise, but everything else is across that power MOSFET, which means it's going to be getting hot pretty quickly. So but yep, it's handling it, it's stable. There's no noise on the oscilloscope that I can see, and so I'm quite happy with that. I do want to actually make a separate call out to Vishay Precision Group, who provided me these bulk film resistors, both the precision feedback resistors that I'm using on the circuit here. So these precision resistors, they're actually trimmed to 0.05% accuracy. So within the scope of what we're doing here, you may pay a little bit more for them, but I'm using a precision voltage reference, and I'm able to just drop these two resistors in there with no messing around or anything, and trust that they're going to stay stable and they're not going to drift over time. Couple that with a current sense resistor, which is also using the same technology as these precision resistors, but obviously in a more power capable TO220 packaging, you end up with a very, very stable solution. You know, obviously the voltage reference is already stable to a few parts per million over time and over temperature. Couple that with precision resistors that are doing the same thing. The op amps and other pieces of the circuit really have little to do with maintaining the accuracy. Any trimmers and things, obviously they need to be really reasonably stable, but as long as your voltage reference is accurate and your feedback resistor is accurate and stable, sorry, not accurate but stable, then, you know, once you set this thing up, you're going to be able to trust the output of it quite easily, and that's all because of these Vishay resistors that I'm using in my case. Obviously, you know, for your particular implementation, you may not have to use as accurate resistors as these, or you may not be able to spend the money for these because they are a lot more expensive. You know, you're paying pennies for these standard 1%, 5% carbon film resistors, but you are getting up for the high precision versions of these into the $5 to $10 range, and the same for the current shunt resistor, that they, you know, they can be in the $10 to $20 range as well. But if you're building yourself a DC load where you want to be able to rely on adjusting its output to be accurate and be able to either put an internal meter or just connect up an external DMM across the shunt resistor and get some accurate readings as to what you're loading, or if you're doing logging to test the capacity of batteries and things like that, then being able to just quickly put these in and trust that they're going to work is, you know, worth the extra cost of buying them. Obviously, if you're going to be doing mass production, then you would need to consider the bulk cost. But if you're building this thing just for your own use and you want to have it in your lab, then it's definitely worth the investment in my book. And anyway, I want to send out a big thank you to Vishay Precision Group for sending me these resistors to be able to use in my reviews and projects. They help an awful lot, and thank you. So before I go, sorry, I just wanted to quickly show you some of the parts that I'm using for the project. So this is the TO220 precision current sense resistor that I'm using. Hopefully that's going into focus there. Let me put my hand in the way, let it focus a bit better. This is 100 milliohms, and it can handle a few watts, especially if it's mounted onto a heatsink. So you can get bigger ones for more power and things like that, but that's that one. So the main components that I'm using is the REFO2. These come in a little 8-pin package, and you know, they're relatively inexpensive. And then the other one I've got is the dual op amp, which can have 18018 maximum supply, so quite happily work on a 15015 and definitely work on a 12 volt. Standard jelly bean kind of precision op amp or instrumentation op amp will work, but you can probably get away in this kind of circuit with pretty much any op amp as long as it can handle the supply that you're feeding into it. The other parts that I'm going to be using, remember I spoke about heat sinks and things, and I've got this one currently sitting on a fairly standard heat sink, but one of the things that I had laying around the lab from computer work is actually an old CPU heat sink. All right, and the nice thing is it's got a fan on, and all I need to do, this is a big block of solid aluminum, it probably got more heat dissipation even just on the casing than the one that it's currently sitting on. So what I'm going to do is drill and tap a couple of holes in here to mount the current shunt resistor and the power transistor, cut a hole in the back of my project box to basically screw this onto, feed the fan voltage. It takes 12 volts, which happens to be what I'm supplying this thing with, into there, so that when I power this thing up, now it'll have some active cooling to allow it to run at some higher loads. Now I'll have to test it. I've got no idea what the actual degrees C per watt above ambient that this heatsink is rated at, but I'm pretty sure that, you know, knowing that if I put 30 volts at 1.5 amps into the current heatsink, I can't even hold it. This thing looks like it'll dissipate more heat, and coupled with the fan on it should be able to do a lot better. So we'll have to see how well that goes. I will keep that in a future video just to let you know what happens with that. But it's something to bear in mind. If you've got old computers from an old 486 or an old Celeron or whatever, but a decent sized heatsink, some of the ones that you can get are much bigger. And if you're not worried about how big the heatsink or what it looks like, it will adequately keep your power MOSFET. Because remember, most of these modern CPUs, they're running at 150 watts for some of the more powerful ones. So, if you look on Element 14 or on eBay and things like that, heat sinks are pretty expensive. But if you can get an old CPU one that you can use for your DC load, nothing wrong with that. And if it comes with a heat sink already on it, and sorry, a fan already on the heat sink, bonus. Okay, so that's that. And then the last few pieces, sorry, I keep looking away while I grab things off the bench here, that I've got is, here's a small project box. It's just an ABS plastic kind of box. But the nice thing is this heatsink will actually go on the back. If I put it near the bottom, so it'll actually stand up on its own. And it's almost exactly the width of this thing for the actual heatsink. The fan goes slightly wider. But I'll put that on the back of the box and cut a hole out in the back of this to take the little square recess of this. So that'll allow me to mount that quite easily. Using a little 12 volt jack, well, it's not 12 volt jack, but it's a little barrel jack, will allow me to give the 12 volt DC to 15 volt DC input quite easily. And then the rest of the components are basically miscellaneous components, a little bit of variable to put the circuitry on inside of this thing. And then on the front, I'll mount a couple of banana sockets with a standard width so that I can just plug in pretty much anything I like as far as the load's concerned. I'll put the 10-turn pot in the middle here, and then on the top I'll probably put a display for showing what the current is currently going through this thing. I probably won't bother trying to put the voltage on here as well, much as I'd like to, because I think it'll interfere with the current paths and mess that up. But anyway, that's the parts there. So you've seen all the other parts already as we were going over the breadboard. And this is basically what I've had laying around that I bought a while back for a project that I didn't do. So I'm just going to reuse it for this, and it should work just a treat. So I hope you enjoyed that. I will post the schematics and everything so that you can use them for yourself if you wish. I got no problems with you using it, changing it, providing feedback. If you like the video, give me a thumbs up or a like or whatever's appropriate, depending on where you're watching it, and provide feedback if you want to. Okay, thanks, bye.